Thank you for the introduction, and thank you for inviting me to this seminar. And actually, my talk connects quite nicely to the previous one because it's also about machine learning, but rather than considering, for example, crystal structures, we're looking at more disordered systems, and in particular at inhomogeneous fluids in equilibrium and in non-equilibrium. And to start off, I want to first talk about the equilibrium case, where the general question is how to determine the structure and thermodynamics of a given fluid model when it is subject to some external environment, which may be inhomogeneous. And to do this, of course, you can use simulations. This is rather straightforward, I would say. But the problem is that simulations are in general quite expensive, so you wouldn't want to do this for a lot of external environments, for example, for exhaustive parameter studies. Alternatively, there's classical DFT, which is founded on this minimization principle and which therefore avoids the explicit many-body picture. But for most fluid types, you don't really know the functional mapping which is required here. So this is also has a limited usability in most realistic cases. And our attempt was to connect both worlds by machine learning and by constructing a neural functional which enables to make these predictions ideally with the precision of simulations and at the cost or at the efficiency of classical DFT calculations. So to get an idea of our strategy, let me first introduce you to classical DFT. Like I said, it's found on this minimization principle of the grand potential, which can be expressed in principle exactly as a density functional. So this is already a quite remarkable result, which goes back to Robert Evans. And writing out omega, you can see that it consists of an ideal gas term, an external contribution, and this excess-free energy functional, which captures all the internal interactions of the many-body system. And plugging in omega into the minimization gives us an Euler-Lagrange equation, which looks like this, and which has on the left-hand side the excess-free energy contribution, or rather its functional derivative, which is called the one-body direct correlation functional, C1. But so far, we haven't really made much progress because in order for this equation to be useful, we of course have to specify some functional relationship here. And we can't fool statistical mechanics. Finding such a functional is in principle exactly equivalent to solving the many-body problem. Or as Jascha Rosenfeld, who developed a very famous class of these functionals, once put it, the problem with density functional is that you do not know the density functional. So quite a devastating statement. And to make progress, you have to think about other techniques than analytic theories. And of course, machine learning comes to mind. So in machine learning, we have to first generate our reference data. And this equation actually provides us with some guidance because it's quite straightforward to obtain for each relevant quantity a simulation result. And this is done simply by inputting an external potential landscape, running a simulation, and then sampling the density profile. And together with knowledge of the chemical potential, you can just calculate the C1 profile pointwise for each position. So in this slide, there's really no DFT. This is just a simulation exercise. And to make this more concrete, we look at the hard sphere fluid as our example model. And on the right-hand side, you can see some of our simulation results. So we're in planar geometry to make things easier and just come up with some inhomogeneous external potentials along with some values for the chemical potential. We run grand canonical Monte Carlo simulations and get the density profile from which we calculate C1 in this pointwise way. And for machine learning purposes, we split our simulation data into a training set, a validation set, and a test set. This is just standard practice. So switching back now to the DFT way of thinking about the many-body physics, we know that C1 isn't just this pointwise thing, but that it rather is a genuine universal functional of the density profile. So in principle, knowledge of this blue curve enables us to calculate or to infer this yellow curve. And of course, we use machine learning to do this. We don't want to write it down ourselves. And in particular, we use a local learning strategy. So instead of mapping one profile to the other as a whole, we focus on a specific point and devise the neural network to output just the scalar value at this point. And it does this by taking as input the density profile within a certain window around this point, which takes into account that C1 is in general quite short-ranged at least for short-ranged interparticle interactions. And well, I'm going to spare the details of the machine learning technicalities, because this is really just a straightforward, fully connected network, and it's just a standard regression task. But having done this, we have obtained a neural representation of the functional mapping from rho to the one-body correlation function. So this neural network is actually the starting point for many relevant applications. And as a first example, I want to show you neural DFT, which is just the prediction of density profiles as you would do in usual DFT, but using our neural functional as a surrogate for C1. So we have to do this self-consistent iteration, for example, by using the mixed Picard iteration. And instead of providing an analytic result for the C1 functional, we just plug in our neural network. And this gives us a rather straightforward way to predict density profiles. Here I'm showing the typical scenario of a hard sphere fluid adsorbed against a planar hard wall. And the result is as you would expect. Now, a particular advantage of doing this mapping in a local way is that we got rid of the system size of the training data. So despite this functional being trained on rather small simulation domains, in the application in neural DFT, we can just increase the system size virtually to arbitrary sizes and predict multiscale problems. And as an example, I'm showing here the gravitational sedimentation-diffusion equilibrium of the hard sphere fluid. So just by applying linear gravitational potential. And as you can see, neural DFT resolves the correlated structure near the boundaries, as well as the slow decay of the density profile within the sedimentation column, which, by the way, follows an equation of state. More on that later. So now you might ask, well, this is a density profile, sure, but is it the correct one? So how good is neural DFT really? And for this, we have done some error analysis with the simulation data of our test set, which hasn't been seen during training. And we've set this up as a quasi-exact reference and have compared various state-of-the-art DFT functionals and the results from our neural functional in the prediction of density profiles. And both in a global error and in a local error, the neural DFT outperforms both of these functionals. So this is already quite a success, because the hard sphere fluid is actually one of the few types of fluids where available approximations are actually quite good. Now, predicting density profiles isn't the only application of the neural functional. Instead, I want to show you that it's also rather straightforward to come up with a functional calculus. And there are two directions you could go. To get to free energies, you have to do this functional line integral, which is just a line integral in function space by parameterizing this input of rho. And to get higher order correlations, you just apply functional derivatives. Now, both of these procedures can be done with the neural functional. In this case, it's just a straightforward evaluation of these integrals. And in the case of the derivative, we can use automatic differentiation as commonly used in other machine learning tasks and for the training of the neural functional already. to just derive the output with respect to the density input. And this gives us C2. Now, to test this neural functional calculus, we go back to the bulk fluid, which might seem a bit counterintuitive because it's about inhomogeneous fluids. At least that's what the training data consisted of. But actually, the application to a bulk fluid reveals already if the neural functional can extrapolate, because bulk fluids haven't been contained in the training data. So this is already quite a hard test. And I'm showing here the derivative, C2, which due to being in bulk only consists of one free coordinate. And I'm not going into the details of this liquid integral equation pipeline. What's important to see is that we can get to the static structure factor, which might be quite surprising because it's quite an insane way to go there, really, because we started with a mess of planar inhomogeneous systems and now obtain something which is almost G of R, basically, and which is radial. But nevertheless, this sets up a comparison with the Perkisiewicz theory and with simulation results. And including our neural functional results, we see that the static structure factor follows quite accurately by this liquid integral equation pipeline. In particular, here you can see the deviations to the Perkisiewicz results. Now, in terms of the integration, in the bulk fluid, the free energies are connected to the equation of state. And for the hard sphere fluid, the equation of state is well known. There are multiple analytic approximations, in particular the Carnot-Starling equation of state, which is quite accurate. And again, there are multiple ways to get to the equation of state, starting from the neural functional, either by determining the free energy or by going back to the two-body results. But no matter how you do it, you get results which lie basically on top of the Carnot-Starling equation of state. In fact, the lower panel zooms in on the deviations to the Carnot-Starling result. And you have to remember that this is not an exact equation of state. So we have consulted further reference, which stems from very accurate simulations done by these people. And our neural functional up to the metastable region basically reproduces these results. So we have achieved without much effort, just by running standard grand canonical Monte Carlo simulations of randomized systems, a simulation-like accuracy of the equation of state, which is quite nice and which verifies again that the neural functional together with the functional calculus really works. So to conclude for the equilibrium case, we base our machine learning on a representation of the one-body direct correlation functional in terms of a neural network. And this enables us to solve common problems of predicting equilibrium fluids. So the neural DFT gives us access to the density profile, which is also applicable to multiscale problems. And the neural functional calculus enables us to investigate the structure and thermodynamics of both homogeneous and inhomogeneous fluids at low computational cost. And this has been exemplified for hard sphere fluid, and the neural functional has been trained with planar grand canonical Monte Carlo simulation data. If you want to try out some of the methods, we have provided a topical review and a tutorial which exemplifies these techniques for the 1D hard rod system. So give it a try. Now, for non-equilibrium, things might look not that promising at first because classical DFT is well known and it provides us with this minimization principle. But what about non-equilibrium? Well, we need two ingredients. We need, first of all, a one-body description of the internal interactions and correlations which arise in such systems. And we need to somehow functionalize some relations within this one body description. So if we consider Brownian dynamics, which is, for example, relevant for colloidal systems, then we can derive from the many body picture a one-body force balance equation, which is given here. And in fact, if you compare this to the equilibrium case where we have the DFT Euler-Lagrange equation, you can see that this is just a generalization of this equation, which is obtained simply by taking a gradient and setting v to 0 for the equilibrium case. But in general, of course, in a non-equilibrium, the velocity will be non-zero. So what remains is to find a description of these internal forces, which are really the only non-trivial part that we have to consider. And this description must be some functional theory. And fortunately, power functional theory provides us with the existence of this mapping, which includes, beside the density profile, also a functional dependence on the velocity profile, which is due to being in non-equilibrium. And I won't go into details here, but it's just important to know that this is, again, formally exact relation. For general time dependence, it includes the whole history of these profiles. So it seems easy if it's written down like this, but this can actually be a very complex object. And in particular, it contains contributions which can be associated to an equilibrium-like behavior, the adiabatic part, and a super-adiabatic part, which captures the truly non-equilibrium forces. So, having guaranteed the existence of this functional mapping, we can now proceed similarly to the equilibrium case and obtain first of all training data, for which we simplify again a bit, because first of all, we don't want to deal with the explicit time dependence and the dependence on the history of these fields. Rather, we want to work with steady states, and we want to, again, simplify to a planar geometry. So in this case, we consider the Lennard-Jones fluid and run adaptive BD simulations by just inputting, again, randomized external landscapes, which are non-conservative in this case, so given by some force profile, and getting out from the simulation a density profile, a velocity profile, and the internal force. So this is exactly what we need to be able to infer this functional mapping. And this is again done by constructing a neural network in this local sense that it outputs only the values at one specific point when it is given the information of the surrounding profiles. Besides rho, of course, here also V is relevant. But then the training just proceeds similarly to the equilibrium case. And it's basically, technically, it's from this point on the same thing, apart from the output, of course, consisting of a vectorial quantity, also the velocity profile. So what can we do with this neural kinematic functional? Well, it's relevant in each application which requires to predict non-equilibrium forces accurately. And these are this is a very broad class of problems. Either it's just the straightforward application to get some results for this fint profile. More interestingly, we can also solve inverse design problems, which we call custom flow. And we can also use it for a time evolution. I'm not going to go into details in all of these points, but I'm instead focusing on this inverse design idea, which is basically, just to restate a problem, which is basically just prescribing a certain form of rho and V and asking what is the external force that we need to generate this specific non-equilibrium flow. And by rearranging the force balance equation, we can determine F external. But in general, if you don't know the internal force, then you're stuck at this point. But of course, that's where the neural functional comes in, as it gives us a direct way to access this information by providing it with the desired density profile and velocity profile. And just to exemplify this, we have come up with some non-equilibrium situation, which is characterized by this specific form of the density profile and these components of the velocity profile, which have to fulfill the continuity equation, by the way. And we can just ask the neural network to give us, for this specific situation, the internal force, which also has these three different components. And that's all we need to evaluate the right-hand side and to get a prediction for the external force that is required to generate this non-equilibrium situation. And to test if the prediction was correct, we can run a many-body simulation, adaptive BD again, and see if the external force, which serves as input to the simulation, recovers the desired form of rho and v. And I'm switching back and forth here, so you can see it does this quite nicely. And just to demonstrate that you really need sound description of the genuine non-equilibrium effects that go on in the system, I'm doing here the adiabatic, super adiabatic splitting. So remember that this is the interesting stuff. This is the non-equilibrium part. And as you can see, it's quite substantial. So it's non-zero and it influences the concrete form of the internal force very strongly. And if we didn't get this contribution right, as is the case, for example, in dynamical density functional theory, which by construction neglects this part, then we wouldn't be able to do this inverse design correctly. So with that, I want to sum up what we did. We have used neural networks to represent certain functional mappings, which are given in equilibrium by DFT and in non-equilibrium by PFT. And these neural functionals have been trained with randomized simulation data, in equilibrium obtained by grand canonical Monte Carlo simulations and in non-equilibrium by adaptive BD. And having obtained such a neural functional, we are able to make very accurate predictions of the internal correlations and forces which these systems appear. And these neural functionals are not only used for straightforward predictive tasks, but also in various other ways, for example, for multiscale problems, for functional calculus, and for inverse design problems. And with that, thank you for your attention, and let me know if there are any questions.